So each time I do it, I get a little bit more careful. But I don't slow down, so that's out. When we look at, we're used to seeing this. Two aluminum solids, well, I'm used to seeing this. 2 aluminum solids plus 3/2 O2 gas yields Al2 aluminum oxide solid. So what we're doing here is we're taking the elemental form of each of the 2 reactants, combining them to make a product, right? When we do this, we have a delta H of formation. So that F is delta H of formation, heat of formation, right? We also know that delta H of formation, which is just what? Q at a constant pressure. So delta H of formation. Now when we do this, most of the time, this is for a metal plus a nonmetal, which is also known as an ionic bond, delta H of formation is a negative number, or is negative, let's say, is negative. Or exothermic, which means it's lower energy. So you have these 2 elements here, they combine, now they're at lower energy, so energy is going to be given off. Now the process of Born-Haber says that we take the elemental form and we bump it up to the gaseous state. And then we create ions, and those ions come together and make a crystal lattice. Okay, but this isn't in ionic state, this is in elemental state. So the process involves steps that make each reactant gaseous state and ionic. So to start with aluminum, aluminum's a solid. We want it in the gaseous state. What we do then is we say Al2, oh, let's keep it nice, Al2, or 2Al, right? Because there's going to take 2 aluminums to do this. So every process we're looking at, well, I'll get to that too, is we want to go to 2 aluminum gas. All right, so that's the step we're looking at. This has a delta HF, but it's not called delta HF anymore because we're not going from the elemental state and forming a product. We're going to put energy in to atomize, or I call it sublimation, and old textbooks do too, but a lot of the new ones call it atomization. And depending on the table where you get your heats of atomization or sublimation, because sublimation is going from a solid to a gas. But anyway, we're atomizing this. So we would have a delta H of atomization, but it'd be for just 1 aluminum, right? We're doing 2 aluminums, so we have to do twice as much. So 2 times delta H of atomization. Now we're not doing anything to the 3/2 O2 gas. Right, we're not doing anything to that, so we just bring it along for the ride. But usually, in order to take a solid to a gas, if it didn't take energy, it'd already be a gas. So it's a solid, we're gonna have to put energy in there. So this is an endothermic, or delta H, A, or atom is greater than 0, right? So positive number. So we're gonna go up in energy from this starting material reactant. Now we've done that. Okay, so the next step then, to get this into a usable form, right? We have oxygens double bound, right? You can't activate them that way. You got to break that bond and have individual O's so you can turn them into ions. So what we have here is an oxygen double bond, and we have 3 of them. So we want to break that bond 3 different times and use half of what's in each bond. So there's a total energy associated with the bond and breaking the bond. When you break that bond, each side of the bond or the homolytic cleavage gets half the energy. If you use both of them, it gets all the energy, but we're only using half of them 3 times. You could do 2 bonds and use 2/3, but we're not doing that, or three halves. So we're gonna break the bond. We call that bond dissociation energy. Bond dissociation. And all that means is we're breaking the bond energy. And it'll be in a table as BDE. And there'll be, for every double bond or single bond imaginable, like you can have a CH bond, it has a certain energy when you break it. You have an OH bond, it has a certain energy. But we can only use half when we know how the energy is distributed. So that's why homolytic cleavage, which means 2 of the same elements on the bond. So H2, we could use half of the H2 energy. Why? Because the energy is shared equally between the similar elements. So we're going to do that 3.5 times. So we break that bond, and now we get, oh, my bad. Oh yeah, that's 3 halves. We got to do this. Sorry about that. So not as good right here. I forgot to put the step in. So now the next step, there we go. The next step is 2Al gas. We don't do anything to aluminum now, which is weird for me to jump back and forth between them, because normally I take aluminum all the way up and then do it. The 3O gas. So this is the BDE, I'm sorry. Bond dissociation energy. Okay, and we're going to use that, 3 halves of that. And we look that up on a chart, just like we look up delta H atomization, but you have to know what you're looking for, right? Because obviously in the chart I give you, it's going to have it for aluminum, it's going to have it for oxygen. Just to confuse the matter, you have to know how to spot it. So now we have both elements in their ground state as a gas, but they're not ions yet, right? So they can't come together yet because you haven't exchanged electrons. So what we do is, I'm going to move it over here now and drop down and just pretend this goes up from here. And this is just a repeat step. I'm going to put repeat here. Let's put, not repeat, that's not a good idea. What can we call that? Continuation. Continued from last step. So we have aluminum gas plus 3O gas. All right? So we could pick either one to turn into an ion, but let's start with aluminum. And there's 2 aluminums, right? So we're going to do this step twice. We're going to take aluminum, and we're going to make it aluminum plus 1 plus an electron. And then we're going to leave the oxygen alone. Well, going from aluminum to aluminum plus is called ionization energy, right? You're creating an ion, and it takes energy to remove that electron. And we're going to do that same thing twice. And the first time you do ionization energy, i.e., we call it ionization energy 1. So, and that could be an S or a Z depending on what country you're from. Ionization energy. And sometimes I do S and sometimes I do G. I mean, S or Z, I should say. Ionization energy 1. So when you remove an electron, so now this is going to be a 2, right? Use ionization energy. It takes energy to remove that, so we're going to go up in energy again. Right? And we're going to get this number from a chart. But that's not what we're used to seeing. Aluminum's a 3+, so we're going to have to do a second step where we take off a second electron. So we do that. Al2 plus plus. Now we have 2 electrons. Now we have 4 electrons, because we added 2 more. And then the oxygen's just tagging along for this step as well, because we're only focusing on the aluminum and making that into a cation. So we do that one more time. So this is ionization energy 2, and the third one, guess what? It's going to be ionization energy 3. Now, each time we take an electron, that number is going to be different. The first electron comes off pretty easy, the second one takes more energy, and the third one takes even greater energy. And that'll be reflected. Again, you're not calculating these, and I'm not going to change the problem because we don't have that much time into solving for something other than what we've already seen. We're going to solve this problem for delta HF, I believe, or lattice energy. Might go either way. So now we add IE, and we get 2Al3 plus 6 electrons, right? Because we just added 2 more, plus the 3O gas. And we should have that in brackets. And this is a gas too, right? So that should be there. Always have states. Why do we need states? Why did I work on states so much? Because if you don't have the states, it gets very difficult to understand what's going on and why you have to keep track of them. But you always have to keep track of them because that's where they happen. So now aluminum's ready to react, right? It's 3 plus, but the oxygen isn't. So let's bring, we can go from here. So when you have the oxygen, now we have to convert the oxygen because it's still in its elemental state as a gas, right? So we're going to use one of these extra electrons and add it to the oxygen. So we're going to take one of these 6 and add it, or basically 3, right? So then we have 2Al3 plus 4E, or 3E, sorry, because we're going to use 3 electrons and we're going to add them to the oxygen. And that's a gas. And that's a gas. All right? Well, that costs energy. So, and we call this electron affinity. But we're not used to seeing O2. O2 is what we want, not O1. So we're going to have to do a second step. But this one costs us energy. We gained energy there, but this step, 2Al3 plus no E plus 3O2 minus, right, is electron affinity 2. So the addition of a second electron. And all these numbers are going to be in a table that you pull out, but you'll have to know which one goes with which. So EA2 is a positive. So the first one, it adds the electron very easily, drops to a lower state, but to add the second electron costs us energy. So we go back up. And now we're in the state we want to be, right? We have 2 cations, 3 anions. They're going to form this lattice and go right back down to, where is it? Oh, it's all the way over there. Right, so this is going to look sloppy, but the whole thing is we're now going to weave through here. We're right there. And this is our lattice energy. So the change in heat due to coming together as a gas all the way to the product. Now, conceptually, how do we get there? We want HF. So HF is down here. All right, we started, here's the lattice energy. Wait a minute. Let's start with our steps. So we're here at HF minus. Then we're going to add, what do we add? First thing we add is delta H. What? What's the first thing we did?
Sublimation.
Yeah. Or sublimation, right? So now we're going to go up. So we went down, HF went down, now we're going up. And as we go up, the next thing we do is bond dissociation, right? Then we're going to add, oh, how many times did we do this? 2. Heat of atomization, aluminum. BDE, oxygen. Now we're going back to the aluminum, and we're going to, what's the next step? Yeah, 3 times IE1 plus 3 times IE2 plus 3 times IE. Whoa, just 2, right? Or is it 3? It's 3, right? There you go. So now we've got our gas atomized and aluminum ionized. So we broke the oxygen bond. Now we have to subtract, or it's not really subtraction, right? It's add the negative EA1. And how many times? 3. Oh, this is all wrong.
Isn't it for the oxygen?
Yeah, it is. This is aluminum. We're only doing it 2 times, but we're doing it 2 times each step, and there are 3 steps. So let's start over. So the first step, what, is delta HF, which is a minus number. Then we're going to add, right, delta H atomization of what? Aluminum. Then we're going to break the bond of oxygen, 3 halves. Then we're going to do 2Al, 2 ionization energies for aluminum, plus 2 ionization energies of aluminum, plus 2 ionization energies of aluminum. And that gives us aluminum plus, aluminum.
Wait,
2.
why'd you do 2 IE2 twice?
He meant to put a 3.
Oh, okay.
Sorry. All right. And now we're there, and then now we're going to do 3 electron affinity ones for oxygen. Then we're going to do 3 electron affinity 2s for oxygen. And then lattice energy.
For electron affinity 1, is that plus -3?
Yeah, it would be. It'd be, but whatever that would be like this. And a lot of times, so there's a different way of doing it that where I usually take the positive steps and the negative steps, the favorable steps and the unfavorable. But this, we're not getting there. We don't have enough time for that. So, and then all that together, right? What happens now? Does the lattice energy add to that or subtract from that? Does it include this? So we add the lattice energy. Okay.
Isn't it heat information plus lattice energy equals all the rest of those combined?
Well, we had it up on the board the last time.
Yeah.
Yeah, there was 2 different ones though. I can't remember which one it was.
So,
I think it was E lattice equals all of that.
so if we look at the steps, we're here in elemental, and then we drop down to go to HF. And then when we come back, we're here. So all these steps include, right, where does this go? This is the final step, and it goes all the way back to the bottom. So all these things added together, or if you could put this as plus the minus if you want, equals delta H lattice. And if you swap these two, right, now you have minus lattice plus HF. All right. So I wanted to go through that one more time. Hopefully that was There are also 2 videos that are going to be out too that aren't. It's too bad I screwed up the adding. But remember, if you're just adding them together, you can take the negative and the positive charge as it goes. Right? You're just adding everything in stepwise fashion.
And there's going to be one of these on the exam?
Oh yeah,
Okay.
you're probably this one.
This one's on the practice, yeah.
It's on the practice exam.
Got it.
So
Are you
basically,
gonna draw it out for us like you did on the practice, or are you gonna have us draw it?
I don't know. I might put in a couple of steps just in case. But yeah, you should know the whole process, right? I mean, what I'd really like to do is give you something you haven't seen, but I'm not going to do that. Okay, so the second thing I want to do today before we leave, which we're not going to stay too long. Let me know when everyone's done with the board. Are you guys done?
Yeah.
The second thing is about reports and how we've been doing them and how normally I'm much more conscientious about what I make you turn in and how to do it. But we're just back from not doing anything in person anyway. And I didn't realize there were 3 different lab books, so I'm going to make a bunch of excuses here. But
Yeah. We're just trying.
and I let it get, and then I had the COVID and some health concerns. Kind of lost my mind, but it's back. All right, so let's look at experiment 13. We're going to be doing acid-base titration. So this is what we're doing Thursday, and we're preparing on Tuesday. So if I was going to start making a lab report, I would give my title and I'd call it experiment number 13, acid-base titration. But I wouldn't put titration techniques. I'd read a little bit and say, with KOH, right? Would I say that? I don't know. Let's look. Because that would separate me, right? KHP. There we go. KHP. Acid-base titration with KHP. And then you could also throw in and technique. Right, that makes it my own. Now it's not like anybody else's because I looked at the title and then I went into introduction. So depending on your lab book, now normally I would go over this in detail prior to the end of the semester, but again, Danae wants you guys to have a little bit better lab report writing skills than what she had this semester, so I want to make sure that we address that. If there are pre-lab questions, they would come next. And let's see if there are any. Right, so this is me doing it without knowing what's going on, right? That's the whole idea. You're just doing what I'm doing without knowing what's going on. Because you haven't seen it, how would you know? So you're gonna look at 13, and I'm gonna keep my little fidget spinner right here. And then I'm gonna find, did anybody see any pre-lab questions?
Yes.
Uh-oh. So now I know that I actually have to do that. Pre-lab assignment. Right, is that 13? Uh-oh. Oh, here it is. Well, shoot, there goes my bookmark. See, I'm just like everyone else, or not quite really. Pre-lab. Okay, so, redraw the structure of KHP. So I would do that. And then I'd write the formula, calculate the molar mass. So redraw KHP. That's going to take me a while because I'm not that good at drawing hexagons. Uh-oh, there I go again. And then, does it have conjugated bonds? We don't know what that means, but yes, it does. It means every other bond is a double bond. So there's some organic chemistry for you. And then it's got a C double bond O coming off of this carbon, which would be carbon 1. All right. And what else we got? Oh, it's the carboxylic acid group. All right. So that's what that looks like. And then there's another one right here. Is that the same thing? Yes, it is. Only it has the actual carboxylic acid attached to it. There we go. So 2 carboxylic acid groups, and there's the K plus right here. So this is minus, then the K plus right here. That makes it ionic, right? But it's in solution, so it dissolves. And that's it. The rest of these are H's around here. So we'll draw it just the way it looks here. And then what do I have? 1, 2, 3, 4, 5 H's. So H5. How many carbons do I have? 1, 2, 2 outside the ring, 6 on the ring. That's 8 carbons. And then I have 1, 2, 3, 4 O's. All right. So now I have 12.01 times 8. 5 times 1.008, 1.008, and then 4 times 15.999. Right? So 30 or 32, 64, and 5, 69, and 96. So whatever that is. So now I have a molecular mass, right? Somebody wants to do that. They
Did you
can.
also add the K?
Oh, yeah, you should, huh? But remember, this is this. And that's that. And then the K would come first, right? But now, let's just rewrite it. Right, so that's a minus, and then, so this would be K plus, and then I do that in my lab book, right? I do K plus C8H5O4 minus. And let's see. Make sure I got it right. 1, 2, 3, 4, 5. Yes. 1, 2, 3, 4, 5, 6. Yes. 7, 8. Good. 1, 2, 3, 4. Good. And a K. So whatever that is. Look that up. Oh, and they already give us the formula. I didn't have to do that. H4. That's not right.
Just because they have an H behind them.
Oh.
KH,
Oh, okay. But it's not KH. Whatever. Okay, so that's that. And explain why it's soluble in water. Using the ideas of intermolecular forces. We didn't even talk about intermolecular forces. But remember, the solubility, water is polar, and this compound is ionic, so polar solvents dissolve ionic solutes. So that would be my C, and it'd be pretty short like that. I wouldn't really go into great detail. I'd say something about like dissolves like. This is an ionic compound. Most ionic compounds are soluble in water because water is polar, meaning the oxygens are charged negatively and the hydrogens are slightly positive, which allows the water to get in between the crystal lattice of the ionic substance and dissolve it. Number 2, right? We know how to do that. Calculate the volume of a 5.5 molar NaOH needed to prepare 1 liter of base solution of the concentration used in this laboratory. I want to look at that one. So part 2 would be, and again, how neat does it have to be? Well, that depends on you. For me, this part of it, I know somebody has to read it. So I'm going to try to, for me, I'm going to try to make, and that doesn't mean it's going to be neat. It's just, for me, it's going to be as neat as I can do. Right, so that was 1. Here's 2. 2 we already know how to do. 2 is using the equation. So what is that? That's, we're gonna skip that, right? That's the net ionic, because I don't want to spend a bunch of time on this stuff. But basically, I do want to do number 3, which is M1 V1 equals M2 V2, and we know M1 is 5.5 moles per liter, and we want to know question mark V1 equals, and now we need to know V2 is 1 liter. And then we want to know what we're going to use in this experiment. And does it tell us? Sodium hydroxide, 0.1 molar. So M2, 0.1 molar NaOH. Volume 2 is 1 liter NaOH. And then molarity 1, 5.5 molar NaOH, and question mark V1. So we just put this in here, 0.1 moles per liter, and now moles equals what moles equals liters, right? But no, that's not it. They equal each other, so they all cancel out. That's what. Yay. What?
He read further. He read further into it.
What happened?
I said, where'd you get 0.1?
Oh, that's from the experiment. That's what we want to make.
Oh.
I've got that from the reading. Right, so that's what you have to do. You have to read the experiment before you do the experiment. It's not just going and copying down the experimental procedure. That's why we have you do the pre-lab portion. So that's why I think this is important, which is why I'm spending a few minutes doing it, so that we're ready. So calculate the mass of KHP needed to react with 25 mils of 0.12 sodium hydroxide. So this is another point, which means we have to get our KHP ready, right? We have to know what that formula is, and I'm going to let you do that. You can either look it up or however you guys do it. It doesn't really matter. I want you to get that equation and then calculate this. I'm not going to use our time for that because that's something I think you should do outside of class. So now we've done the pre-lab, right, in terms of what I think. So what comes next? Well, what comes next then is the, somebody tell me, purpose. What are we doing this for? Right, so purpose. Now I don't know. I haven't looked at this, so I'm gonna see what I think the purpose is. That's going forward here. Sodium hydroxide. Okay. So primary standard, secondary standard. Why not use carefully diluted? So it seems like the purpose is to. Does anybody have an idea?
It's the objectives, no?
I think it's the objectives, right? Right. So I would try to make it. I would try to say something like what?
Just reword this.
Yeah. So to become familiar with the purpose is what? Threefold. That's what I would say because there are 3 steps there, right? The purpose of today's lab is threefold. This is just me writing, and you can copy this, but please don't use it because I don't like the way I write. Purpose threefold: to demonstrate. No, not to demonstrate. To what did I say before? Gosh darn it. Demonstrate proper techniques. So familiarize. To familiarize students with titration techniques. I don't like having students in there. To become familiar. Right? And so you're trying to eliminate pronouns and references to people. because the reason you do that is to try to eliminate bias. Everybody has bias. There's bias involved. But we're doing our best to separate our writing from the bias. So, to become familiar. Now, that was just my start, is threefold. First, to become familiar with titration techniques. Second, use techniques to determine unknown molar mass using, and now I'm going to slip in, I know something, sodium hydroxide base. And then what's my last one? Finally, back titrate and antacid using standardized reagents. All right, so that's my purpose, and it's all in my own words, okay? But it's using what was exactly there. And now I'm moving on. Now I'm gonna do some, what? Theory, if it needs to, right? And it does. This needs some theory. And what is theory?
For this one?
Yeah, for this one.
Discussing what titrations are used for?
Yeah, we're gonna look at titration, right? We're gonna say titration is a volumetric technique, and titration allows us to accurately determine concentration using a standard. I'm not going to write that down, but there it is. And then you could talk about, we'll be using primary standards and secondary standards. Okay. And we're going to do back titration. And the principle involves, if we know the concentration of one reagent and the volume we use, we can use the molecular equation and the stoichiometric ratio between the reactants to accurately get the determine the concentration based on the volume of the unknown used. And that's our theory. And I'm not writing that down. But that's the kind of thing I want to read, right? That says, oh, I read the introduction. I know what we're using. I know what we're doing. That should all be done well before you get in lab, just like I'm doing right now. And I'm not going to spend an hour. How much? I've been here like 10 minutes already. That's it. 10 minutes. For a 3-hour class, I've spent 10 minutes so far. All right. So that's theory. Now can I go to? Now I'm going to take the procedure. I've already done that in front of you guys before, right? Yeah. Where I took the words. So theory, rehash, intro, using formulas and theory, and what do you call that? Background, equations, terminology. And then procedure, right? In your own words. Why in your own words? Because now you're familiar with what you're doing. If you're just copying it from here to there, you might as well just print it out, because you're not thinking about it. But if you have to turn the procedure into your own words, now you're actually making a difference. And does it take a little bit longer? I don't know. Let's look. I'll do a little bit.
This one might take a little bit.
What's that?
I typically add for like step one being a paragraph, what I write is typically like three sentences. I condense it down into just the core steps. For like the procedures.
Okay, well, whatever helps you to be able to, because here's the idea. You take your lab book, you already know the procedures, you just look at them to refresh your mind. You shouldn't even need your lab book, because your lab notebook should have your procedure written in a way that you can do the steps with no other reference.
Exactly.
Because if I'm going to follow you behind you, and you write this thing and I don't know what it means, and I can't use it to do the experiment, it's of no value. You might as well not even have done it, right? But if you do it beforehand, now you've got the steps in your mind that you've done, and you recognize them again because it's in your language. You come in here and you just do what's written down, because you already know what you're going to be doing because you've looked at it. And really, it doesn't take that long. All right. Anyway, was I going to do some steps? I was going to do some steps. Maybe I'll do some steps. Here we go. So again, here we are. And this is a complicated one, which is why I'm saying you really need to look at this one if you want to get good results. And on this one, I'm going to grade you based on your results, just like you were a real chemist, right? And that's gonna, we're already having troubles, but we shouldn't be able to pass lab without being able to follow a lab and without being able to do the techniques that we're looking at. So I want you to, when you're doing this for the next, till we're done, basically, I don't know if I'm gonna even do anything else besides these after this, because we're so near the end and I wanna give you a little bit of time to get the new material. So we'll do this experiment for sure, and we'll do it carefully and repeatedly. So you're gonna have more than one trial with this. All right, so we're gonna prepare 1.1 liter of approximately 0.12 molar sodium hydroxide ourselves by diluting the 5.5 molar solution. So the pre-lab already gave us this, so we should know exactly what we're gonna be doing when we do it, right? We should already have calculated how many milliliters we have to add to our 1 mil volumetric flask to make this standard. All right. But that's what I mean by, that's what I'm thinking about the experiment now, right? Whoa, what am I gonna do? Well, the first thing I'm gonna do is make this solution. Well, how do I do that? Oh, it's the dilution that I did in the pre-lab questions. And I know that's a lot, right? Most of us just show up here and go, okay, well, I forget, what are we doing? And that's to be expected, right? But when you get to 151 and you do that to Danae, hi Danae, it's a 0, right? She's not fooling around, because you get through this to the next one, now you're saying, oh, I am a chemist. I can do this. I'm going to move forward. And so you have to act like you've already done that. And that's why I want us to do that at least one time this semester. So make sure you know how to do this. And then I'm gonna go over it again before lab, because we can't be making that kind of mistake in here. All right, so that's our procedure. Now, observations and data. If you have the tables ready to go, that's great, because that says, oh, I know what I'm looking for. Hopefully you know what you're looking for before you start doing the experiment. You've done a procedure. So with a titration, we're gonna have a known amount, and we're gonna keep track of, a known molarity, and we're gonna keep track of the volume until we get to a certain point where things are neutral, where we make water, right? And then the other thing, we're gonna have a known amount, but we're not gonna know the concentration. So it's kind of fun, right? It's a puzzle. All this stuff is puzzles. You know, if you like to play computer games, then this should be fun. Should be. Doesn't mean it will be. But that's what we're doing. We're taking a known concentration, and then we're determining the volume, and we're taking a known volume, and then determining the concentration. And that relationship is what we're looking for. So we're going to do observations all along the way. We're going to be looking for color changes. We're going to be looking for lasting color changes. Why we look for color change? Well, normally we'd say that's a sign of a reaction, and it is, but it's not a sign of the reaction we're looking for. It's a sign that we're getting close to having done the reaction. It's an indicator of our reaction. The reaction taking place with the indicator is a reaction, but it's not the one we're looking for. That's just giving us the pH, and that pH change is an indication that we're making water, because we're starting with an acid or a base and then approaching neutralization, which is about a 7 pH. So if it's less than 7 in the pH, it's going to be clear, and if it's more, it's going to be another color, or vice versa, depending on what you use as an indicator. So we need to know what color we're looking for with our indicator as well. So that's an observation, that's data, right? We should be expecting, like, okay, if here's a step that you don't necessarily do that I do, right? So I'd say, oh, my base is 0.1. So how much would I be looking for if my acid was 1.0, or my acid was 0.5, or my acid was 0.1? What volume would I be looking for in any of those ranges? And believe me, you can start narrowing it down. If you think your volume of acid is 1 molar, it's going to take you a lot of drops to get to 0.1, right? If you think your acid's at 0.1 and your base is at 0.1, you're probably going to be very close to equal amounts, right? So you might want to start on the other side, where you think your base is 1/10 of your acid, so that you don't run out of acid while you're titrating. So titrating is just adding drops of known to drops of unknown. That's all it is. Okay.
Thank you.
So now we've done all our data, we've written down all our numbers. We're going to take those important numbers, and we're going to write down everything we see when we're doing it. Like, wow, 15 drops in, nothing. This is lame, right? Put in your stuff. Whatever keeps you focused on what you're doing. Had a great conversation with my cross the lab neighbor. Missed the end point. Oh well. Gonna have to redo the whole thing. All right, observational data. And then you do the data and calculations. So this is writing stuff down. During experiment. So this is going to be like the sloppiest of everything, right? It's not going to be your go-to. This is going to be your wow, I did this, and you might get a drop of something on there, or because you're writing in your book while you're doing something and you're noting. Like anything that's time related, you note. Anything that changes temperature, anything that indicates anything has changed, you write it down. Why? So that when you go to write up your report 2 months from now, 2 days, you can recall the details more. That's what it is. You should be able to walk away from your lab notebook, come back in a week, look at that and go, oh yeah, I remember that now, right? Because it's a recollection of what happened. And the greater detail you use, the more irritating it is while you're doing it, but the better it feels when you go to write up what happened, right? We made a mistake back there. I poured in, what was it? Did I pour in too much acid or too much base? I don't remember. I wrote down I poured in too much, but I don't remember which one, right? So you want to detail everything. Added extra acid. Well, how much extra acid? Or spilled the base. Spilled the base so it may not titrate evenly, right? Those are all things that could happen. Oh, I noticed while I was doing this, I couldn't control how many drops I got at a time. Like the least amount of drops I could do was 3. Or I've got, while, you don't say I, but while titrating, was able to split a drop or have drop hang on tip of like that. Or one drop rolled down the edge of the Erlenmeyer flask and it sent the whole thing way out of line because I wasn't able to catch it. Or whatever it is, you're just constantly noting what happened so that when you go back, you can make sense out of what you're going to tell the person about your experience. And that's all that is. And then we get to the data, and so better notes, the better. More descriptive. That's not put better. More descriptive. More descriptive notes, the better. All right. So now we're done, and we want to make sure we know what we were looking for. What was the purpose, but what were we trying to identify? So that we should always be looking for that the whole time we're doing it. We want to know an amount of unknown for this experiment, right? We want to calculate the concentration of the unknown. That's it. That's it. Right? So we want a table that has those calculations available to us. So what's that going to be? It's going to be a highlight. It's going to be moles, volume, right? And I don't even have to look to know that's going to be contained in there, because that's what we're trying to determine. So if you do data and calculations and it doesn't have that, that's not what we're looking for. You need to put it in there, right? You need to put in the highlight of what we were trying to do. And if you don't know what we're trying to do while we're doing the experiment, that would be a time to involve the instructor. Right? What are we actually looking for here? Because if you don't know what you're trying to get out of an experiment while you're doing it, it's going to be very hard later to make sense out of what you were trying to do when you were doing it. So we want to be aware of what we're trying to do before we do it, not after we're finished. Right? Now that's not directed at anyone ever. Right? It's just something to keep in your mind while you're going through this last experiment with me before you move on to your next invention. Or punishment, depending on how you look at this class. So, for data, all calcs. And then finally, what is the last thing? Calculations, all calcs. Especially the important part. The reason, no, not reason. Because that ties back to that purpose, and it's not really the purpose, especially the important data. Right, that's what I should be able to find, right? That's why we have the tables and the boxes, because that highlights the important data. It's not just about putting things in boxes. It's saying, this is the important stuff. So when we're writing down things in the boxes when we're doing the experiment itself, in observations, that's what we're going to keep track of. That's all of it. But then we're going to have another portion where we say, these are the important results of what I did. And then what's the next? Graphs, blah, blah, blah. That's part of that. Okay, summary table of results. It's almost like a duplicate of the best table you have. It's really highlighting the part in the data collection. I don't even like to separate that. I consider that part of the data. So you do all the data, and then you take the best data and you put it in a table. And you don't really even have to separate it, right? It's not really a separate part of the results. It's the results based on all the data you did up here, all the work, all the manipulation. Then you have your table that says, I'm the important part, I stand out. And then you go back and say what you did, and that's the conclusion. And it should look something like, using the threefold purpose of today's lab, acid-base neutralization was studied along with titration to calculate the unknown, and then give how much that was, whatever that was, the molar relationship, and then highlight why it may not have worked, right? Sloppy technique was involved in breaking the burette and having Hollis yell at me, or leave the room and pound his fist and stomp around and then come back in crying. But whatever happened, right, you write that down, whatever calculations, and then and the conclusion, you're also going to throw in like an analysis. How close was I? Was it reproducible? That's when you use your table that's in the back of this lab manual that has, and I really should have done this the first week. I don't know what the heck's wrong with me, but I figured you guys could read. I mean, I still think you can. I just meant I thought you'd do it on your own. On tape. Good job, Hollis. On tape, right there. So, significant figures and statistical analysis, treatment of data. And what's important here is what I like to have in my lab reports is the standard deviation and a confidence limit or a percent error, or all three, right? It's up to you. Like, and you know how I am. You have all three, that's probably a 22 out of 20, right? Because all I'm looking for is one, probably, right? Just show something that says, I looked at this data, I ran it through some kind of analysis that says, hey, I did a pretty good job, or I did a horrible job. I don't really care which one. In this experiment, I want you to do a good job. This one counts, right? So probably out of the 20 points, 5 of it's going to be how close did you get to the unknown. The 5 of it's going to be how well I think you were prepared, right? So this is one is all qualitative in the how I think you're prepared. There's just me thinking that. There's no real way of putting that in a rubric. It's based on my interactions with you during this next experiment. Do I feel like I can turn you over to Danae? Because you got to pass both the lab portion and the lecture portion. And from what I've seen, most of you are going to be there. But I'd like to have you turn it up just a little bit so that, and I know you're all capable of it, but I'd like to see you turn it up a little bit and show me that if I say, yeah, you can go to 151 without having to repeat, that you can go to 151 and no one's going to say, oh, well, yeah, you're not prepared, and so you're out, okay? And it's because it's not fair to you either. And it's not fair to Danae, it's not fair to you. It's totally fair to me to let you go ahead, but I'm not teaching the next level, so there you go. And that's it for the report, right? Oh, right, and then the supplemental. So if there's supplemental, if there is, then you do it. If there isn't, then you don't do it. So supplemental, I don't like the way that is worded anyway, but if there's supplemental, do it. If not, don't. Here's the other thing. If, moving forward, if it doesn't include, when you go to the next lab and there's something that you've done in the lab before, you're probably going to need to do it again, right? It kind of goes without asking. Here's the system that we use, and now we're going to go to another experiment. We're going to use the same system, and then we're going to go to another experiment. It's all about the reproducibility aspects, and it goes along with taking charge of what you're doing, right? Don't wait for someone to give you the chance to take charge of your own education. I'm not talking about anything else. I'm talking about education, right? Take charge of your own education. Take responsibility for what we're going to be doing, and then just do it. Don't go, well, you didn't tell me. Because that, to me, that's like, I don't care. It's the same thing as I don't care. You're here, you care. So take responsibility. Don't put it on me that, oh, Hollis didn't tell me, and that, again, is not directed at anyone specifically. It's directed just as things I've observed over the years that are ways to keep yourself from getting to where you want to be, and I want you guys to all get there. So that's it on lab reports. That's it. If there's any question anybody wants to go over before we call it a day, I'm going to call it a day right now. Okay?